Hello everyone, this is Suryanandu. Now I am pursuing BTech second year in VVIT college. Today my seminar topic is joint movements in multiple random variables in the subject PTSP. PTSP means probability theory and stochastic processes. Let us see the topic joint movements. There are two types of joint movements. They are joint movement about the origin and joint movement about the main. First of all, we see joint movement about the origin. Joint movement about the origin. Let us consider the two random variables x and y. They are expected value of function is represented as g of x comma y that equals to x power n y power k, and it is denoted like as mnk. Mathematically, it represented as mnk equals to expectation of g of x comma y. That also represented we can write expectation of x power n and y power k, and also written as double integral minus infinity to infinity x power n y power k along with density function, where n and k are positive integers. The sum of n plus k is called the order of the movement. Let us see the order of the movements. This is the special case. The sum of n and k is equals to 0. First of all, we take k equals to 0, then n0 equals to expectation of x power n. That is represented like as double integral minus infinity to infinity x power n along with joint density function fx of fx comma y of x comma y dx dy. Similarly, we take n equals to 0, nk m0k equals to expectation of y power k, that is represented like as double integral minus infinity to infinity y power k along with joint density function. Let us see the zeroth order of movement in joint movement about the origin. This is the zeroth movement about joint movement origin. Substitute n equals to 0, k equals to 0. That is m00 equals to expectation of x power n and y power k. That is represented like a double integral minus infinity to infinity x power 0 y power 0 along with joint density function. Since x power 0 equals to 0 1 and y power 0 equals to 1, that is represented like as m00 equals to double integral minus infinity to infinity fx comma y of x comma y dx dy. This is the area under the curve. That is area under the joint density function is equals to 1. Let us see the first order movement when in joint movement about the origin. We can first order movement is taken the sum of n plus k equals to 1. If consider this is taken as two cases. First one is n is equal to 0, k is equal n is equal to 1, k is equal to 0. Another one is n is equal to 0, k equals to 1. The sum of, in first case, sum of those is 1. Next case, sum of n plus k equals to 1. Thus, M10 equals to expectation of x equals to x bar. That equals to double integral minus infinity to infinity x into fx comma y of x comma y dx dy. Next case is M01, that is represented as expectation of y. Expectation of y is known as mean of y, that equals to double integral minus infinity to infinity y along with joint density function. These represent the mean value of x and y. Let us see the second order movements in joint movement about the origin. Second order movements occurred when n plus k equals to 2. Let us consider first case, n equals to 0, n equals to 2, k equals to 0. That sum of n plus k equals to 2 plus 0, that is 2. Second one is n equals to 0, k equals to 2. The sum of n plus k equals to 2. Third case is n is equal to 1, k is 1. Sum of n plus k is 2. Let us see the case 1. Joint movement about origin is represented like as M20 equals to expectation of x square. That represented like as double integral minus infinity to infinity x square along with joint density function. And second case is represented like as M02 equals to expectation of y square. That is double integral minus infinity to infinity y square into along with joint density function. Let us see the third case. This is the special case in second order joint movement. This is M11 equals to expectation of x, y. That is double integral minus infinity to infinity xy fx comma y of x comma y dx dy. These are the second order movements important for mean square and correlation. In second order movements, first two cases are mean square. First case is mean square of x, second one is mean square of y, and third one is correlation. Correlation is important topic in PDSP. We see correlation in signals and systems also. Correlation is a measure of relationship between two random variables, tells us how one variable changes with respect to each other. As we see in signals and systems, correlation is a measure of relationship between two signals. In PDSP, correlation is measure of relationship between two random variables. They both are similar in PDSP and signals and systems. Let us see briefly in importance of correlation, how correlation occurs. Consider two random variables x and y are second order joint movement M11 is called the correlation of x and y. It is denoted as RXX. RXX is equals to M11, that is equals to expectation of x comma x and y, that is also equals to minus infinity to infinity, integral minus infinity to infinity, integral minus infinity to infinity, xy along with its joint density function. Correlation represented in discrete random variables shown below. Rxy equals to summation n and summation m xn ym p of x comma y of xn comma ym. Correlation occurs when in joint movements in second order joint movements two random variables x and y denoted by rxy. For continuous random variables defined using double integral with its joint density function, for discrete random variable defined using double summation with joint PMF. Properties of correlation. If two random variables x and y are statistically independent, then x and y are said to be uncorrelated. That is, Rxx equals to expectation of xy that equals to expectation of x, expectation of y. Proof. Consider two random variables x and y with joint density function fx comma y of x comma y and marginal density function fx of x and fy of y. If x and y are statistically independent, then we know that fx comma y of x comma y equals to fx of x, fy of y. The correlation is rxy equals to double integral minus infinity to infinity xy f xy of x comma y dx dy. We like fx comma y of x comma y dx dy. We split this into fx of x, fy of y. Then Rxy equals to double integral minus infinity to infinity xy fx of x, fy of y dx dy. We slip the integral like this. Then Rxy equals to integral minus infinity to infinity x into fx of x dx and integral minus infinity to infinity y into fy of y dy. Rxy equals to expectation of x, expectation of y. Then the random variables x and y said to be uncorrelated because of expectation of x, expectation of y are statistically independent. Let us see another property for correlation. If random variables x and y are orthogonal, then their correlation is 0. Rxy equals to 0 if consider two random variables x and y with density function fx of x and fy of y. If x and y are said to be orthogonal, their joint occurrence is 0. That is, fx comma y of x comma y equals to 0. Therefore, the correlation is Rxy equals to expectation of xy, that is equals to double integral minus infinity to infinity xy along with its joint density function, that is equals to 0. Rxy equals to expectation of xy, that is equals to 0. Hence, it is proved. Let us see the second topic in joint movements is joint central movements, and it is also called as joint movement about the mean. Let us see the joint central movements. Consider two random variables x and y. The expected value of the function g of x comma y is equals to x minus x bar whole power n, y minus y bar whole power k are called joint central moments, mathematically represented as mu n k is equals to expectation of x minus x bar whole power n, y minus y bar whole power k, that is equals to integral minus infinity to infinity integral minus infinity to infinity x minus x bar whole power n, y minus y bar whole power k along with its joint density function, where n k are positive integers like 0 to infinity. The order of the central movement is n plus k. Let us see the zeroth order central movement mu 0 0. Mu 0 0 is equals to expectation of 1 for continuous random variable. Mu 0 0 is equals to integral minus infinity to infinity integral minus infinity to infinity 1 into x fx comma y of x comma y dx dy, that is equals to minus infinity to infinity minus infinity to infinity fx comma y of x comma y dx dy, because the joint PDF probability density function integrates to 1, that is mu 0 0 is equals to 1. Discrete analog 0 0th order central movement for discrete random variable is represented like this. Mu 0 0 is equals to summation n and summation m p xy of xn comma yn, that is equals to 1. Let us see the first order central movement mu 1 0 and mu 0 1. Now we see mu 1 0, that is equals to expectation of x minus x bar. Start with the definition. Mu 1 0 is equals to double integral minus infinity to infinity x minus x bar into fx comma y of x comma y dx dy. We separate the integral. In mu 1 0 equals to double integral minus infinity to infinity x fx comma y of x comma y dx dy minus x bar double integral minus infinity to infinity fx comma y of x comma y dx dy. Sorry for the disturbance. We see from the first order central movement. In first order central movement, mu10 is equals to expectation of x minus x bar. That is represented as mu10 is equals to double integral minus infinity to infinity x minus x bar along with its joint density function. So we separate the integral like as mu10 is equals to double integral minus infinity to infinity x along with its joint density function minus x bar into double integral minus infinity to infinity joint density function. The first double integral is equals to expectation of x because integrating fx comma y over y gives fx of x. Therefore, double integral minus infinity to infinity x into fx comma y of x comma y dx dy is equals to integral minus infinity to infinity x into fx of x dx that is equals to expectation of x, that expectation of x is known as mean of the x. The second double integral is 1. So because of it, double integral minus infinity to infinity fx comma y of x comma y dx dy is area under the curve. Area under the curve in joint density function is 1. So mu10 is equals to x bar minus x bar into 1 that is equals to 0. Similarly, mu01 is also 0. Similarly, we get mu01 is also 0. Now, we see second order central movement that is mu20 that is equals to expectation of x minus x bar whole square. That is mu20 is equals to double integral minus infinity to infinity x minus x bar whole square along with its joint density function. Expand the square. X minus x bar whole square is equals to x square minus 2x bar into x plus x bar square. Therefore, mu20 is equals to double integral minus infinity to infinity x square along with its joint density function minus 2x bar double integral x into fx of fx comma y dx dy plus x bar square double integral fx comma y of x comma y dx dy. Here integral minus infinity to infinity x into fx comma y of x comma y dx dy is equals to x bar and double integral minus infinity to infinity fx comma y of x comma y dx dy is equals to 1 because of it is a area under the curve that is equals to 1. Double integral x square fx comma y of x comma y dx dy is equals to expectation of x square. That we can write in above equation that is like this. Mu20 is equals to expectation of x square minus 2x bar into x bar plus x square bar. That is equal to expectation of x bar minus x bar. We know that variance of x is equals to expectation of x bar minus expectation of x whole square. That is mean square. expectation of x square minus x mean square, that is variance of x. Similarly, mu 0 to we get variance of y. Now we see the mu 1 1 in second order central movement. Mu 1 1 is equals to expectation of x minus x bar into y minus y bar. We can write as mu 1 1 is equals to double integral minus infinity to infinity x minus x bar y minus y bar fx comma y x comma y dx dy. We expand the this product is x minus x bar into y minus y bar is equals to xy minus x into y bar minus y into x bar plus x bar y bar. So we substitute these in equation 1. Let us take this is an equation 1. Sorry. This is equation 1. We substitute this in equation 1. We get like this. Mu 1 1 is equal to double integral minus infinity to infinity xy fx comma y of x comma y dx dy minus y bar into double integral minus infinity to infinity x into along with its joint density function minus x bar into double integral minus infinity to infinity y along with its joint density function plus x bar y bar double integral minus infinity to infinity with its joint density function. From this we get double integral xy its joint density function, we get expectation of xy double integral minus infinity to infinity x into along with its joint density function we get mean of x, and for y we get mean of y. This is the area under the joint density curve, that is equals to 1. We take this is as equation 2. Now we substitute these values in equation 2. We get mu 1 1 is equals to expectation of xy minus x bar x bar minus x bar y bar plus x bar y bar. We combine these terms. Mu 1 1 is equals to expectation of xy minus x bar y bar. We know that expectation of xy is correlation. X bar and y bar are product of mean. This is known as covariance. Covariance is represented like COV of x comma y or sigma xy. For discrete random variable, mu 1 1 is equals to summation n to infinity summation m of xn minus x bar into ym minus y bar into pxy of n comma ym, that is equals to expectation of xy minus x bar and y bar. This is all about the joint central moments. We see mu 0 0 is equals to 1. That is 0 central movement is equals to 0. And first order central movement is 0. And second order central movement, case 1 is variance of x, case 2 is variance of y, and case 3 is covariance of x and y. Covariance is equals to rxy minus sigma rxx minus product of mean of x and mean of y. Let us see the covariance. Covariance is a statistical measure that indicates the degree to which two random variables vary together. If both variables increase or decrease together, the covariance is positive. If one increase while the other decrease, the covariance is negative. If the changes in one variable does not affect the other, the covariance is zero. Mathematically, for two random variables x and y, Cxy is equals to expectation of x minus x bar into y minus y bar, where E is the expected value, x bar, y bar is mean of the x and y. Covariance is second order joint central movement mu11 is called covariance of x and y. It is expressed as Cxy is equals to sigma xy equals to mu11 is equals to expectation of x minus x bar into y minus y bar. In integral form of continuous random variable, Cxy is equals to double integral minus infinity to infinity x minus x bar into y minus y bar along with its joint density function. For discrete random variable x and y, Cxy is equals to summation n summation k of xn minus x bar n into yk minus y bar k into p of xn comma yk. Thank you for watching.